If you do know what a monad is, there's also fine. We have quite a lot of material for people who kind of already have the theoretical grounding as well. In terms of questions, just leave them for the end. We'll have some time at the end to kind of go through stuff. The code on the slides, it is here to illustrate. It may not be perfect production quality every time. I promise it's always gone near a compiler at some point in its life, but that may be a long time ago. And in the course of slide creation, slide editing, they may not all be perfect anymore, but we've done our best. Just to briefly introduce the two of us then. So we're both software engineers at Bloomberg. I think you've heard quite a lot about us this week. And in particular, we work in a division called MARS. So MARS stands for Multi-Asset Risk System, and it's basically Bloomberg's enterprise risk solution. So we price on the order of 1 to 2 billion derivatives every day. And the requirements in the enterprise space are actually very straightforward, right? Firstly, your software must never break. And secondly, your software must be released really quickly. You must release loads of new features for your clients. Very straightforward, but perhaps not the friendliest of briefs. And perhaps those two things are not entirely compatible with each other. So over time, we've developed different methodologies to kind of help us work quickly, but also try and stay safe as well, right? And some of them are obvious, like the use of unit testing. And some of them are a little bit more esoteric, like the use of monads, right? So over the last few years, we've experimented using monads both for safety and also for code clearness. I think it's helped us quite a lot, and that's kind of how we ended up on the stage today. So the game plan for today is basically to talk in 3 parts. So I'll continue talking a little bit about the motivation behind monads and why do we care in the first place. After that, we'll spend a good part of the talk talking about what actually are monads, what do they do, how do they work. I've seen quite a lot of talks about monads this week, and I think they've assumed quite a lot of knowledge. We're going to try not to do that today, and we will try and kind of go from the ground up. And finally, once we have kind of theoretical grounding, then we'll go into where are they actually being used in the STL, where are they being used in the wider world, and maybe some clue toward the future of C++ itself. So just before I hop in, just to get a feel for the audience, who has heard the word monad before? Who has attempted at some point in their life to understand what a monad is? Who knows what a monad is? They're very brave, Brian. Brian, what's a monad? I'm being mean.
I understand what a monad is. You asked if I know what a monad is. You didn't ask if I could explain what a monad is.
Yeah. So yeah, I'll come to this in a second, but this is part of it. I'm not really sure what the confusion really is, right? Monads are simply monoids in the categories of endofunctors. They're very straightforward. Some of those words are very straightforward, like a and the. So this is a fun quote. This is some category theory. We're not going to go anywhere near this for the rest of this talk. You can confuse your friends with it, but while this is a completely correct statement, it's not very relevant to software engineering, in my opinion. The more interesting point around the definition, which is kind of why I stung Brian with here, is what's called the curse of the monad, right? So this is from a guy called Douglas Crockford, who, among other things, is known for the invention of JSON. So the idea of the curse of the monad is, in addition to being good and useful, it's also a curse. And the curse of the monad is once you get the epiphany, once you understand that's what a monad is, you then lose the ability to explain it to anyone else, which is maybe not very encouraging for me stood on the stage at the moment, but that's where we are. I think there is quite a lot of truth in this. I think they are quite difficult to understand from definitions. And I think we're going to take a different approach today. We're not going to try and kind of explain it from a pure definition point of view. We're going to basically work it up from the ground using examples and code. I think that's a more easy way of kind of understanding roughly what it is. And my goal really is to have more than 1 or 2 hands in the air by the middle of the presentation, but we'll see. So as I said, monads are impossible to understand with definitions, but now I'm going to put up a definition anyway. So if you go to Wikipedia and put in monad, this is basically what you get. You get quite a large block of text. I'll read through it briefly, but it's not very useful in my opinion, right? So monad is a structure that combines program fragments and wraps their return values in a type with additional computation. In addition to defining a wrapping monadic type, monads define 2 operators, one to wrap a value in the monad type and one to compose together functions, and then some more kind of boilerplate, right? So who understands what a monad is now? Yeah. So I think this is actually quite a good definition. This is completely accurate, but it's not a concept you can easily kind of grasp purely from a definition point of view. But I pulled it up anyway for the last part, right? So I've highlighted a few of the kind of nice words here, right? So monads reduce boilerplate, they introduce succinct pipelines and they abstract away control flow, right? So this is really the motivation for this, right? Monads are cool, sure, but this is what we actually care about, right? Getting rid of boilerplate, having nice pipelines, and getting rid of control flow, right? When I think about C++, many different words come to my mind. Succinct is not one of those words, right? It is one of the problems the language has. And maybe it's not the most short and brief of languages to work in, right? And really the goal with this stuff isn't to be cool, but it is to try and make C++ a little more friendly and have slightly more succinct code and reduce your possibility developers can kind of introduce errors through control flow and this kind of thing, right? So as we go through the slides, to try and keep this stuff in mind, right? This is really the goal, and this is why we're doing this, right? To make our code a bit more simple and to make it a little bit harder for developers to write bugs. So that's kind of why we're here. I'll hand over to Georgi now to talk a bit about some of the theory behind monads and functors.
Thank you, Alistair. So in this section, we're going to be talking about the concepts. So monads, as known from functional programming, are actually derived from a field of math, as Alistair said, called category theory. And there is a pretty involved theoretical foundation. We're not going to go that deeply in this talk. There's a bunch of excellent talks from previous years if you want to dig into the theoretical part. In this talk, we will cover only what's enough for us to see the underlying design pattern that peeks through the mist of all this complexity. So it will be more software engineering and design-based talk. The example we see are more applicable to the real world and also closer to the real world. Before we move into any of that, I guess I've seen presenters discuss what makes them qualified to give the particular talk. Instead, I want to ask a slightly different question over here. Let's put C++ on the spot. Basically, what makes the language good enough to be able to incorporate those patterns from functional programming? I guess to answer this, when we say C++, what do we really think of? Well, we know it can support a few paradigms as a multi-purpose language, and those are the ones that typically come up. And I guess I'm going to make a bold claim here. As of C++11, we can also have functional paradigm, which is really what's relevant here. I guess what does functional paradigm mean? Well, one of the definitions is functions are first-class citizens within that language. And I think you can say that functions in modern C++ are first-class citizens. Ish. I guess probably not in the strictest sense, and you're going to find people opposing this statement. My personal view, it is the case to a very reasonable degree. And to back up those claims, I guess we can briefly see how functions have evolved throughout the years. Basically starting with plain C functions, which were nothing more, and then C++ came in the game, and we were able to override the call operator on classes as having function objects. And then modern C++ took that much further with things like lambdas and some nice utilities like stud function. And further iterations of the standard improved on that with things like capture initializations with lambdas, generic lambdas, and so on. So overall, functions nowadays play a very big role in C++, much more than in the past. And I believe it's because of this we can discuss those functional programming techniques in C++ without the language crossing all the necessary checkpoints. Now, with that in the back, on to what all of us are here for. What is actually a monad? I guess we're going to get there eventually, but we need to start with something simpler, a thing called functors. So monads and functors are related concepts, often used interchangeably, sometimes even in official documentation, as we'll see. But it definitely pays to understand functors first as a stepping stone to explaining monads, since they're a little simpler. So the question changes slightly. What is a functor? I guess the first thing that comes to the mind to the C++ developer is something like this, basically a class or a struct that has its call operator overloaded, allowing instances of that class to act as functions or callables. Well, this is not what we mean by functors in functional programming. What is it then? I guess here on the lower part of the slide we can put our focus on is we have a semi-formal definition of what a functor is. So you can think of it as a construct or a type which is parameterized with another type A, and it also defines an operation transform. So this transform takes as input a mapping from A to B, and it returns a functor of type B. So note here to just dissect this a little bit. Transform, what we're saying here is really a function that takes another function as argument. And this is something we need to get used to with functional programming in general. But in other words, the gist of this is functors is able to transform itself into a functor of potentially different type. So this is the key takeaway. And I guess there's more to this. There are certain functor laws, part of category theory. We're not going to go that deeply. I have an appendix at the end of the presentation. We'll ship the slides after. And then you can take a look at all of those over there. Here, we're just going to stick to the relevant bits for what we're here for. So this thing over here, could we convert it into something we're a bit more familiar with? So this here is our functor C++ified. You can think of it as a template struct. And transform is just a member method. The mapping we were talking about is just represented by a stud function, taking A as argument and returning B. And a piece of note, transform doesn't necessarily need to be a member method. We can also define it externally like so on a given type. So what does functor mean in that case? It's basically a type for which defining transform makes sense. And this is the key takeaway here. And what makes sense means we're going to see in the following example, I guess. So over here, we want to make stud vector a functor. So note over here that we're focusing on concepts rather than what's happening in real life and optimality. On one hand, vector doesn't really have a transform member method. On the other hand, we're taking things by value here. This is just intentional. We just don't want to overload the slides with optimizations at this point. So that being said, let's try to implement transform for vector. I guess the first thing to start with is to define our output vector of type B, and this is the obvious part. Now, what goes into the rest of the implementation? I guess as Alistair said, functors, monads, in order to be useful, they need to abstract away some common control flow, right? And what is the most common control flow when you think of vector and ranges in general? Well, it is traversing the vector or the range, right? So what we're doing here is we're going through each and every element of this vector, transforming it via our f function, and creating our output vector b off of those transformations. So again, what we're saying, the common control flow with vectors is for loops in that case, and here we're just pulling that up into transform. Now, how is that useful? We're going to take a look at an example. So we're going to be looking at this example throughout the presentation. It's a very simple one. We have a vector of strings that represent numbers. What we want to do is double those numbers and return them again as strings, right? And as good engineers, we've broken down the solution into 3 modular steps, and we've defined the following operations. The first one to convert string to int. The second one is to double an int, and the third one is to do the reverse conversion from int back to string. Now let's see how this would look without the functors. I guess the typical imperative way to do this would be something like that. So we create an output vector, we go through each and every element of the input, we apply the 3 operations in succession, and the final result we add to the output vector, and we return the output vector at the very end. Now note that there's nothing wrong with this code, nothing particularly complicated. It's pretty much what we get hired to do, right? But at the same time, I would argue that there's nothing very exciting about it. And after making these accusations, let's see how that would look with our new functor. So we have this thing over here. We have our inputs. We do the 3 transforms, and that's pretty much it. Note here that each transform is going to return a new vector, and that becomes the input to the other one, right? So we have this pretty nice composition that is kind of reminiscent of the builder pattern, if you know that from the Gang of 4 book. But the difference is we always end up producing a new object in the end. New vector. And another point, compared to the imperative solution, over here we really have 3 for loops. And again, there is a way to fix this with lazy evaluation, but again, performance is not what we after here. I guess what I want to focus on here instead is how beautiful the solution with transform is, right? It's much nicer, more concise, declarative. I didn't have to write any for loops. All of this is control flow wrapped up in transform. And it definitely seems like an improvement from an API and a user experience standpoint to me. Now, I want to ask this question at this point. Is this really the first time we're seeing something like this? I guess this does look familiar, doesn't it? Obviously, ranges, big player in the game, part of the standard now as well. Much superior implementation from what we saw so far with things like lazy evaluations that more or less solve all the issues that we mentioned before. But basically, next time you use ranges transform, just think about the underlying pattern we discussed today. Cool. The next question I have is, we can probably agree at this point that treating vector as a functor is a useful thing. Can we go beyond stud vector? Is something like this unusual? So over here, we still want to double a number string, but this time our number string is wrapped within an optional, not a vector. And similarly, by virtue, the return type of our double numbers function is also optional. And you know, optional, quite an important type. It's been in the standard since C++17, but for example, in Bloomberg, we had our own optional for quite a while before due to its usefulness. And this is how we typically do it. We first need to start by checking if our input optional contains a value. If not, we just return an empty optional, right? Otherwise, we need to extract the value within the optional, again, carry out the 3 steps in succession, and return a new optional at the very end. I'm not going to discuss how beautiful this code is, because it's not at all. I'm just going to go to directly how that would look with a functor. So over here, we have our input. We do the 3 transforms, and that's it. Now, how is that possible? It looks suspiciously similar to the vector example, doesn't it? But this is what design patterns are all about, right? Reusable solutions to common problems, and this is exactly what we have over here. Note here that we don't have a single if and else statement. Why is that? Well, I guess this is control flow encapsulated within transform, nothing different from what we had with the vector as well. And let's take a look at how it's implemented. This time we're a bit closer to reality. There is transform and a bunch of other monadic operations coming to the standard for optional in 23. But a simple implementation is like so. Again, we need to define our output vector of type B. And what about our f function? So we want to call this only conditionally on this having a value, on this optional having a value. Otherwise, there's nothing to call f on, and we just return an empty optional. And this is where this conditional check gets hidden. So basically what happens here, each of those transform, again, is going to call the pass function only if this has a value present. Otherwise, the empty optional is just propagated through the pipeline all the way to the end. Now, looking at the second option, I think that the argument for optional functor is even stronger than the one for vector. Why is that? Well, we started with this nonlinear control flow of having to always check the presence of value. And we managed to completely abstract this away within transform, and we ended up with this beautiful linear pipeline, which is a big positive. And not to mention also that forgetting to do your null checks on a pointer is quite dangerous. And here the functor pattern completely removed that possibility, right? We don't have any if and else checks. Now, are there any performance concerns over here? I guess each transform is going to do a null check. So a little bit more overhead, and keep that in mind. The recommendation always stays the same. If performance is of concern, you should always benchmark usages of high-level constructs like this functor operations over here in your code. Now, by this point, you might ask yourself the question, why should I care about this, right? I'm pretty sure I'll never forget to do my null checks, and everybody in my team is the same. We're 10x developers, right? All of us. Well, here is a small proof that you might be wrong about this. So I don't know if you can understand what those things are, but those are basically PRs from one of our repo that more or less fix issues with unguarded access to optional. They have actually led to disasters on prod. Undeterministically, hard to reproduce, hours of developers' time spent on that, right? So really the big thing here, from a software engineering and best practices point of view, if something is repetitive and boring, I'm definitely going to forget to do it. And if it's dangerous to forget to do it, such as doing your null checks, then we have an issue, don't we? So definitely functors are useful, but they're only half of the story, right? And I'm handing it off to Alistair again to speak about something a little bit more different.
Thank you. Cool. Okay, so that was functors. I think in practice in our code, we probably use functors more than we use monads, right? I think for most use cases, they are actually what you will end up using. The monads, the category theorists are going to hate me for saying, but monads are basically a special case of functors for some certain edge cases. By and large, functors are kind of the thing that you'll find yourself using most of the time. So if you take one thing back to work next week, that's not a bad one to take with you. So as I said, the monad, what it really gives you on top of the functor is basically the ability to deal with some edge cases. And the best way of illustrating this is basically to bring up an edge case, right? So let's start with look where the functor may start to break down. This is one of our examples, right? So this is when we were trying to convert effectively a string to an int, double it, and then convert it back to a string again, right? So we defined these three operations. We sketched over one of the details at the start, right? So the first operation, convert string to int, obviously isn't a total operation, right? Not every string can be easily converted to an int. If I give it a 1, it should probably give me a 1 as an int, right? If my input string is bananas, what's it going to do, right? And from this type signature, it's actually not obvious what's going to happen, right? Maybe it'll just throw an exception. Maybe it will just return a -1. Maybe the program will just crash. It's very hard to say, right? There's a whole other talk about error handling I don't want to go into now. But let's say I'm going to, as a developer, make a decision to change the error handling style slightly. So I'm going to return a optional int instead of a regular int, right? So if I pass in bananas, I should get back null, right? It's kind of fairly clear enough from the API how my thing should work. So we're going to try and do that, the optional example again, right? We start with an optional string, and then we go through the pipeline. I've made a small change here. Luckily, C++ is very friendly, so these small changes shouldn't really impact my pipeline very much. So I'll just kind of run the pipeline again, and then the compiler blows up with a very incomprehensible error message. This specific one is from the GCC implementation of the C++23 std optional. I am not going to try and read it for now because it's a lot going on, and it's probably easier to look at the code to figure out exactly what broke, right? So this is our std optional pipeline, right? So the one-line recap on transform, what it's doing, you give it an optional of type t, you give it a function from t to t2, and it gives you back a optional of type t2, right? So our function convert string to int is now a function from string to optional int. So when I do transform, I start with an optional string, and I get back an optional int, right? Because the return type of the function was optional int, I get one more level of optional. So it's an optional int. And then I go to the next step, right? So I say, okay, I want to do double int. Double int is a function from int to int. So transform unwraps the outermost optional, takes an optional int, and then it's going to throw a compile error, right? Because you can't pass an optional int to double int. So if we look at the compile error, sorry for your eyes, but if you look at the second to last line, it is telling you this in a very cryptic way, right? So it's basically saying, when I'm trying to invoke a function from int to int and I pass an optional int, I get some compiler magic, right? I'm not a compiler whisperer, so I can't tell you exactly what it's saying, right? But fundamentally, this is what it's complaining about, that you're using an optional int, or using an optional int where it's expecting an int. This isn't very good, right? I quite like my pipeline. I want to use my new convert string to int, but I also want to use my pipeline, right? How do I fix this? So if I just pull up the actual types that are in play, I'll give an advanced warning now. There's a slightly circular explanation. I promise there is a good payoff at the end of it. You have to bear with me for the next kind of 5 to 10 minutes. So there are 5 types in play, right? There's string, there's optional string, int, and optional int, right? So I can go from string to optional int by doing convert string to int. I can go from optional string to optional int using transform of convert string to int. But what I actually want to do is go from optional string, which is my input, to my optional int so I can continue my pipeline, right? And as we can see from this diagram, there isn't actually a way of doing that right now, right? I'm kind of blocked. I can't kind of get where I want to go. So as a software developer, I'll just kind of make the thing I need, right? So if I've got this kind of red arrow here, I can go from optional int to optional int. And now I can get from optional string all the way to optional int using these 2 arrows, right? So this is kind of the high-level direction. So what actually is this red arrow? How do I go from an optional int to an optional int, right? As you can imagine, this actually isn't a particularly complicated operation, right? So let's just define an operation called join. So what join is going to do, basically, is take in an optional and convert it to an optional. This is hopefully quite a straightforward operation, right? If my outermost optional has a value, I return the innermost optional. If my outermost value has no value, I just return null, right? So it's effectively collapsing one level of the structure. So I turn optional into optional. This is kind of the core, one of the core parts of how the monad works. Does anyone have any problems with the code on the screen? I hope not. It's only 5 lines, so I hope it's okay. So now I can kind of make this pipeline work, right? So I can go from optional string to optional int via transform, and I can use join to go down from optional int to optional, right? So I can now kind of get the pipeline to work again. So if we look at it in code, the pipeline is still kind of here, but it doesn't look very nice anymore, right? So I do the first transform. I go from an optional string to an optional int. I turn my optional into a regular optional using join. And then I just call transform a few more times, right? So I'm kind of back where I started. It looks a little bit ugly, but the fundamental pipeline is still in place, right? So this is kind of okay, but it doesn't look very nice, right? You'd think maybe we can make it look a little bit nicer. So maybe I'll introduce a new function, right? We're going to call it and then for reasons that will become clear in a second. I'm just going to do basically 2 things, right? I'm going to call transform as before, but then I'm also going to call join to get rid of the nested optional. So you'll notice with the signature of and then, it only works if your input function is returning an optional itself, right? So you get this nested optional in your kind of first step, and you can join on it. So now I'm going to do the dangerous part of the presentation. So who understands how a transform works in an optional? More hands than before. Who understands how join works? So that's all a monad is. It's a transform followed by a join, right? So once you understand what a functor transform is, and you understand how a join works, that's all a monad is, right? So if I just kind of bring the pipeline up to make it look clean again, this is my pipeline again. So I do an and then to do the transform and the join in one step, and then I do some more transforms to kind of finish off the pipeline. So the big takeaway, what a monad is, it's a transform followed by a join. If you remember that, you can't go wrong, I hope. So I've done one example. Let's just do another one just to kind of hammer the point home a bit. So actually, I've got a few more slides. Introducing the monad first. So a monad is basically all the requirements of a functor plus one more operation. In C++, this is called and then. The reason effectively has been an optional has been standardized. This and then name was basically chosen as the name for the monadic bind. As far as I know, for some reason, C++ has got like a unique name for this. No one else is using this name. So functional languages may call it a monadic bind, an M bind. I think in Scala it's called a flat map. It's got many names, but C++ we've got and then. And it's basically a transform followed by a join. So if you compare it to a raw functor, they look incredibly similar to each other, right? So transform for a functor, you take in a function from A to B and a functor of B, and get a functor in A, and you get a functor of B. And for the monad, it looks very similar, but your transforming function on the bottom right, the return type is itself a monad. This is basically the only difference, right? So with the example for optional, your return type for and then has to be an optional. And we can hammer it home with one more example, right? So the other example is vector. So vector, probably the most common type you run into when you're using C++. And actually, it can quite easily be turned into a monad as well. So really, monads are everywhere. So before I kind of jump into how monads apply to vectors, it's good to build out some motivation, right? So with kind of the vector functor we saw earlier, or stood transform, which is basically what a vector with the functor is, your mapping is 1-to-1, right? So I give it a vector of size 20. When I transform it, I have to get back a vector of size 20, right? This is kind of how stood transforms always worked. It's how functors fundamentally work on list or vector-like objects, right? Your input size is always your output size. Stood transform, of course, is very powerful, but this is a kind of fairly fundamental limitation, right? There are things you can't implement with stood transform, right? Like, if I want to implement a filter, I cannot do it using stood transforms. I can't cut out any of the elements. A monad is basically a generalization of this concept, right? So with a monad, you can go from one element to any number of elements, right? So my output vector size can be anything. So you can basically implement any kind of transformation of a vector you want to do, right? So I can filter a vector, I can produce far more elements in the vector. It's a much more generalized way of manipulating the elements in a vector. So a good way of illustrating this is by basically going through an example. So I'm going to make a very kind of simple toy example using a C++ compiler. I think most people in the room have used it at some point in their lives. The model for a compiler I'm going to come up with is very straightforward, right? So you can give it a file name, and it gives you back to a vector of strings, basically corresponding to a vector of error messages, right? This is basically how most of my interaction with the compiler goes. I give it a file, and they kind of give me 100 lines back, right? This is basically, a fairly simple model, right? So I want to write a program now which just takes in a vector of files and gives me back one vector of compile errors, right? This is kind of, if you kind of squint a lot, it's kind of think how a build tool might work, right? You compile all the files one by one, and you get back basically a list of compile errors, right? So how am I going to do this, right? First thing might be quite obvious. I'm going to do a transform, right? So I'm going to use ranges for this example because it's a bit cleaner. So I give it a vector of strings, and I'm going to transform get a vector of strings using the compile file function. I'm hand-waving, of course, this isn't actually a vector of vectors because that's not quite how ranges work. I'm hand-waving a little bit, just kind of bear with me. But you can think of it as a vector of strings, right? This looks awfully familiar, right? I had an optional earlier, and now I've got a vector of strings. So I want to do something with a monad here. The first step is transform. Anyone from the audience, what's the second step in a monad after transform? It's a join, right? So there you go. This is the second step, right? So I have my vector of errors, I do a join, and you can do ranges too, right? So you can literally go home and write this code today, right? This already works using standard C++. Like, a lot of the inspiration for ranges came from the functional programming monadic world. To make it far less intimidating, they don't really kind of share this a lot. But that's basically what it is, right? So if you go home today and you do a transform followed by a join on a vector, you're writing a monad. So really, they're not that intimidating. You've probably done it at some point in your life before. So let's go through some other use cases. So one example is filtering. The way you'd filter using the vector monad, right, is that for each element in the vector, you either map it to itself if you kind of pass the filter, or you map it to an empty vector if it doesn't pass the filter, right? This would work in practice if you stood ranges filter. It will kind of be much more expressive to your reader. But under the hood, it's the same kind of idea. You can think of it as like a monad. And the other example is using simulations. Unfortunately, anyone who's in Ben Dean's talk yesterday, he had exactly the same example on his slides, but I didn't have time to think of another one, so you get to see it twice. So I hope most people in this room have at least heard of the game of chess. Some of you may have even played it at some point. And this is basically a simulation to help us simulate a chess game, right? So to introduce a bit of the early code, this is kind of how you might think of the state of a chess game, right? So you've got players, we'll say the black player and the white player, and there's kind of 4 states your game could be in, right? You can become a winner with the first 2 states, you can be in a stalemate, or your match can be ongoing, right? And then you've kind of got the state of the board, which kind of tells you where the pieces are, be some kind of matrix representation probably. Your game state, telling you the state your game is in, and the current player. And then you have a constructor, which basically says, what does the board start look like at the start of the game? So you start, white is the turn player, you're in the ongoing state, and you've got your pieces lined up at each end, right? I haven't implemented all this because it would take a lot of time. And then the kind of real kind of core thing is you have a function called evolve board, right? So you have the state of your chessboard, and then obviously your chessboard itself can evolve into many different states depending on all the moves the turn player is allowed to move, right? So evolve board you can think of is what are all the next states of the current board, right? And obviously this is basically a one-to-one mapping with the state of chess, right? So what I want to do now is write a function so I can say, hey, I've got a chessboard. What are all the possible positions the board can be in after 50 turns, right? And so how do I do this? So again, this may start getting a bit boring at this point, but I pass in a vector of states, all the states that were possible in the current number of turns. I evolve all the states to get all the next states. I then join together to get one vector. And I do ranges too, just to kind of turn it into a concrete output. So what does it look like in kind of concrete code? This is a bit imperative. It's not very kind of cool and functional, but it's quite illustrative, I think, right? So I start with like the board in its initial state. What does the board look like at the start of the game? And then I just take, simulate out 50 turns. And each turn, I'm evolving the boards. And at the end of it, I look like I have all the boards after 50 turns, right? Again, going back to the start of the presentation, there is very limited control flow here. It's kind of very kind of smooth pipeline. I mean, there aren't many for loops. Even this for loop at the bottom, I've kept it in to keep it the illustration simple. But even this, you could remove using some kind of range construct, right? There's not much control flow. It's kind of easy reading the code to figure out what each step is meant to be doing. And ideally, if there is a bug, it's quite easy to spot because there really isn't much code to look at in the first place, right? It makes it a bit easier for developers to kind of see kind of how the code is meant to operate. Just going to take us back to some of our earlier motivations in terms of why we were doing this. So just to wrap up this section then. So what are kind of the common types of monads? So we've taken about two of them today. The maybe monad, which is the optional monad in C++, and the list monad, which is the vector monad in C++, right? These are kind of two of the kind of common types because optional and vector are quite common vocabulary types in C++. But there are many other examples, right? The most infamous one from the Haskell world is the I/O monad. Who has heard people say that functional programming languages can't do any I/O? Yeah. this is the answer, is the I/O monad, right? This itself hasn't really made its way into C++ yet, so there is a proposal out there somewhere for stud future to be adapted to be more monadic, but it's not really broken through. And then the reader, writer, and state monads are basically different ways of manipulating state in a functional program. We're quite good at manipulating state in C++, probably a little bit too good at manipulating state. So again, it doesn't quite have the same kind of use case as in a functional language. We've experimented a little bit with these three internally in our own code, but I think it's nothing really worth presenting at this point. So we haven't spoken about them today. So this is kind of, I guess, some of the use cases of monads in the real world. And that takes us to the end of the theory section. So I can hand back to Georgi to go through some of the use cases in the real STL and the real C++ world.
Thank you, Alistair. So up until now, the talk was based on concepts. In this next and final section, we're going to go through what's available to us within the standard and also look at a small case study, actually, of building our own monadic library. So let's start with what's out there. Some of those things we already touched upon, starting with one of those, stud optional, very important type in the STL. Semantics, quite simple. There's either a value or no value. It was introduced in 17. Unfortunately, though, we only get monadic operations in 23. So as you can see, quite the lag between introducing the type and acknowledging the usefulness of viewing it as a monad. For those, we have and then and transform, which we already looked at, and also or else, which basically takes a lambda that gets called if the input optional is no. So this is how it looks from C++ reference. Over here, we can notice the nice composition of those things, right? And this or else in the end really acts like a catch-all, basically ensuring that the end optional always has a value. So it's always safe to the reference on the last line over there. So pretty neat. Overall, stud optional is great and is becoming greater. Another very popular one is stud expected. I guess similar to stud optional, the difference is it embeds an exception component as well. So the semantics are you either have a value or exception. Coming into 23, and hooray, monadic operations, same version of the standard, which is great. A short example over here, which I wrote, meaning it's available with some compilers already. Parsing a number is the one we're looking at. So basically assume that this can actually result in several different types of errors, and we want to propagate it to our callers by means other than throwing. So we can use stud expected for that. From there over here, in the client code, we can call transform, and afterward transform error, which gets called if we have an error, of course. And we also have or else as a catch-all over here. And we can obviously notice the beautiful composition of all of those over here as well. Next worth mentioning, if you aren't yet on 23, and in fact as early as C++11, there's an open source version for both of those. So Cybrand built those libraries, shout out. And they're monadic from the ground up, and in fact, they have inspired some of the features in their standard counterparts. We use CL expected quite a lot in our code bases, for example. Moving on to stud ranges, I guess those definitely need no intro. We've talked about them a lot this conference and before. They came in 20 in the standard. However, I would argue that iteration wasn't complete. The full usefulness, I think, comes at 23, where some nice utilities like the ranges to conversions come as well. And obviously, those are based on the ranges v3 library built by Eric Niebler, which is a feature-complete library. And we should actually be encouraged to use the one from the standard as much as possible. But for cases that aren't yet on 20 or 23 yet, such as ours, we definitely use ranges v3, which works just great. Now, on to something a bit different, hopefully more interesting, stud future. So we've had this in C++11, and this basically is a type that provides the mean to access the result of an async operation on a type T. A bit of background, most of you might be aware, but a future actually doesn't exist on its own. It's part of the promise future async abstraction. So we got a promise on the sender side, and the future is on the receiver side, and all the kind of state required for the concurrent synchronization is encapsulated in this abstraction or the channel over here. And a future on its own exposes a method to access the result called get, which typically blocks unless the future is immediately fulfilled. Very brief example over here. So we are on the sender side, we have this async algorithm, and we start off by creating a promise and a future immediately off of it. And this future is what gets returned on line 10 from this async algorithm. However, there is an async operation over here represented by this detached stud thread that at some point in the future sets the result on the promise, right? And this is how it looks on the consumer side. So we basically start off by kicking off our async algorithm and then calling get, which again is going to block until the promise is fulfilled on line 7 on the other snippet over there. Now, there are two fundamental issues with future over here. On one side, we have get, which blocks always, right? And this is the only interface that future exposes to access the result. And this isn't really great for fully async applications, right? The other one is to do with the fact that there is no composability possible here, which is also known as continuation in async programming. So continuation is when I get the result of one async operation, and then I want to immediately kick off another one, and so on and so forth. And this is really the ideal architecture of async programs, right? If you're ever going to block in an async program, you don't want to do that until the very last of those chained async operations is scheduled, right? Now let's take a look at an API extension for future that can help solve this issue. So assume over here that we have a future T1, right? We should be able to continue that future with continuation A that looks like this one over here. So basically something giving us the means to transform the result within our original future. And this is what we achieve with this then method, imaginary then method of our future. Now, hopefully by now you guys can appreciate that we have the functor pattern over here, right? Achieved via this then continuation. And another option, as I was mentioning, a future's result can actually immediately roll into another future, right? Immediately kick off another async operation. And this is where we have this continuation B, and we use the then continuation as well for this. So what do we have here? Can people guess? What is this continuation B? It's a monad, right? So we return the same type, basically, or the same wrapping type, stud future of T2. So overall async programming should really look something like this, right? Similar nice pipelines such as the ones we saw for vector, optional. We should be able to basically schedule all the async operations via this, right? And only in the end call get, thus blocking the main thread just once as opposed to each and every time. Now, what I'm showing over here is actually rooted in reality, right? There have been some attempts to fix the future pattern, and I'm pointing out to some resources over here. Feel free to take a look. They're quite interesting. I guess, unfortunately, this didn't happen. And one of the issues, or more like a missing point, is where does the then continuation actually execute? Is it on the consumer side or the producer side, or perhaps neither of them, some other thread of execution, right? Ideally, the kind of feeling in the community is the programmer should be able to specify where should things execute, right? Which is not the case with this API over here. So this is where the stud execution framework comes in, right? So this is basically quite an ambitious research, the goal of which is to come with a new async framework of the language. And over here we have things like senders and receivers, though they're much more explicit within stud execution. And also the concept of generic async algorithms, right? Which is what this then continuation monad really is. It's just an async algorithm. And we also have the concept of schedulers or executors over here that basically define the where and how of async execution. So sounds really great, but there's one bad part about it. It's still work in progress, not going to make it in 23. And at the same time, we still have this broken future pattern in the standard since C++11. And I'm not really being over picky or pedantic here. In my team, for example, we've often shied away from using future due to those limitations that we mentioned. Gonna finish up this subsection with a really cool paper. You guys might not be aware of it. Hopefully makes it in C++26. I'm gonna call it P1255 due to the long name by Steve Downey, a person in Bloomberg. So it has two new features. We're gonna go over one of them here. Basically a view allowing us to lift nullable or optionals to a range-like interface. And this is called views nullable, right? So maybe like types or nullables, such as std optional, pointers, perhaps things like finding an element in a container, right, should all work with that. And from then, we can use range features. In this example over here, this for loop is going to execute only if the original optional has a value, and it's going to execute at most once, right? So as you can see, all of a sudden, we have this extra safety for maybe like types, which is great. We're able to unwrap them. And how is that possible? I'm going to briefly explain the mechanics of how this works. I think it's an interesting thing to know. So within the ranges library, we have this view interface, right? Which I can basically implement for any type and make any type look like a range, right? So the nullable view looks something like that. So over here, I guess we start by implementing this view interface or subclassing this view interface. And somehow, next we need to wrap on top of the nullable value, whether it's the row pointer, the optional, or whatever. And then the nicest part about it is we need to kind of expose those range-like operations that is required by its parent class, view interface. So over here we can see things like begin, end, size, and so on. And obviously once we're done, we have our original nullable value lifted to a range. And if you really think about it, if you're kind of passionate about design patterns, this is a great example of the gang of 4 adapter pattern over here, right? And this is in fact how all views in ranges work. So things like transform, filter, join, all of those are implementation of the view interface. And I'm showing this here as it will become relevant in a bit. But back to P1255, it might take a moment or two to appreciate, but this basically allows us to implement absolutely anything from what we saw so far. Right? Let's take a look at our double numbers example over here. So the input to the whole thing is an optional string, right? And the very first thing on line 4, we start with adapting that via the nullable view. And then we do 3 things. We first transform the string to int. And since that, and the updated one now returns an optional, right? We again need to adapt that via the nullable view, which is what the second transform is, and join in the end, right? So all of those things are needed to implement and then or monadic bind, since we don't really have one for ranges, as Alistair was saying. But yeah, the other transformations are literally the same. In the end, I guess we need to kind of do this reverse adaptation back to optional, which is what this for loop is for. So basically, this for loop is going to execute and fill out only if doubled has a value as a result of all these transformations, right? So we either end up with an empty optional or something that has a value. So we're pretty cool. It might take a moment or two to see what's happening, but we can use ranges for maybe types, right? The last bit I'm a little skeptical about. I personally feel that something like a ranges to conversion back to optional would be pretty cool. But obviously that wouldn't work in the general case because ranges can have more than just 0 or 1 values, right? So that's the thinking over here. And at this point, I guess we'll wrap up the walkthrough of what's available to us. I hope that we managed to cover the important pieces in the standard. I know there's stuff we must have missed outside the standard, but I also want to spend a little time going over a case study of something which is monads related. So to give the context for it, it is to do with nullables or what I call maybe types. So again, things like std optional, finding an element in a container, pointers, and so on. As we saw with P1255, we can view those as ranges, right? And basically this gives us the whole expressiveness of ranges algorithms, right? Which is a big positive, makes interactions with them safer. But that said, I think there's also another side of the story. I think that maybe types are like misfits in the STL because they don't really have their own formal protocol. And in essence, what we're saying here is that the best thing we got right now to make them exciting is to uplift them to a range. And I kind of find this a little sad. But leaving the emotional side apart, is it not more intuitive to just treat treat optionals as they are? Just optionals or maybe types, right? So for instance, isn't it a little weird to think of optionals in terms of begin and end, right? And also things like size, which typically map onto the set of all non-negative integers, whereas size can just be 0 or 1 for maybe types. An explicit has value API makes much more sense, doesn't it? And I guess other things include things like front, back, and so on, which is part of the range protocol, which I don't think belongs to the optional protocol or nullable protocol. So basically what I'm saying is with the range scheme, we need to kind of have this mapping from the range protocol to the maybe protocol in order to get access to all these nice algorithms. And once we're done, back to the maybe protocol, right? And we saw this with the P1255 example, and I find this a little overwhelming. It's not the end of the world, but APIs, we definitely want them to be carrying as little cognitive load as possible, right? So what I'm alluding to, just as we have this range thing as a concept in the STL, right, plus a bunch of algorithms for ranges, and that's been the case for as long as we had C++. Can we not have the same for maybe types? So just an insertion point here, adaptation to ranges, such as with the P1255 example, isn't misguided at all, and you can see it in other languages like Scala, for example. But maybe or nullable, I feel, is really like a self-contained protocol, and I do think it makes sense to have like an independent native protocol for maybe types, right? And everything else, like range adaptations, should be cool add-ons. So schematically, I think that would make more sense. What I mean is all those things, finding an element in a container, pointers, optionals, map together onto some sort of maybe-like concept of type T1, right? And for some of those, the type, the API of the type maps directly, for example, for optional and pointer. How would that work for something like find? So finding an element in a container typically returns an iterator, right? And in order to denote the presence or absence of value, we need to pair this with the end iterator. So one way we can do this is use the adapter pattern. So we saw that it worked quite well for ranges via the view interface thing I showed, right? So we can basically employ the same strategy over here when building our maybe protocol. Back to this thing, so we have our maybe-like type of T1. We can pass it through our algorithms, which are now specifically designed for maybe types. So over here, we just show transform and then, just 2 of them, but we can have a lot more. And as a result of those transformations, we get a maybe-like of T2. And in the end, we can probably have a maybe-to conversion to something concrete, so something like set optional, for example. And let's just word it out. So we started with a maybe type of T1. We did our transformations, and we ended up with a maybe type of T2, something concrete, state optional. Now that sounds very intuitive to me. And I guess this to conversion in the end, we can be parameterized with other things, not just optional, but for example, unique pointer, share pointer. Maybe we want to disallow things like row pointers, since those are a little more dangerous. But anyway, let's see how this might look in some code examples. So on the top left, we have the canonical by this point example to double numbers, right? And I'm going to use that here as well. And this is with this new API. So a few things to point here. Transform and then are lazy views, and they're only evaluated when the result is requested. In this case, this may be to conversion, right? Composition also looked nice. We've chosen to overload the pipe operator, similarly to ranges. And with that, let's take a look at some variations for this. So we have one where the input is a unique pointer and the output is unique pointer as well. And we have a maybe to conversion to, not row pointer, unique pointer. And we have a maybe to conversion to unique pointer in the end. One where the input is a row pointer and the output is a unique pointer, similarly maybe to conversion to unique pointer in the end. And one over here for find. So this is an interesting one. I guess we have maybe find. And the semantics here are if the search key is found within the input map, we do all of these transformations on the value, otherwise we do nothing, nullable is propagated through the pipeline. So how is that possible? I guess we didn't really implement our own find algorithm. There's just a few things that we need to encapsulate over here. On one hand, we probably want to differentiate between sequential and associative containers. So sequential containers use stud find, which is just linear search, whereas associative containers like maps have find defined as a member method, and it's typically much faster than the linear search stud find would do. And on the other hand, as we said, find returns an iterator, not directly mappable to maybe. We probably need to have the adapter pattern over here. So this last bit is something I find particularly useful. And in general, what we see over here is something similar we have internally within my department, and it's proving to be useful. And because of that, I decided it's a good idea to bring it up here. So basically what we're showing here is a little more refined version than what we have internally, how basically after using it for almost 2 years we'd like the API to look like. Now, we're going to wrap up with check at some of the internals of this thing. I'm not going to provide a full implementation. It's beyond the scope of this talk. But just some of the API and hook-in pieces. So let's begin with our maybe-like concept, right? So what we have internally is something as simple as this. So 2 type requirements. On line 8 is the first one. We want our type to be bool convertible. So we can check for the presence or absence of value. And the second one, on line 9, we want to have the dereference operator so we can access the object stored within our maybe object, right? So stud optional pointers all have this as a valid interface if you think about it. And overall, it is a little simpler than trying to define it as a range, right? Nothing like begin, end, size, front, back members at all. What about our view interface? So what we have internally is something like that. So we have a statically defined interface that basically requires over here derived to be maybe like during construction. And many thanks to Dietmar, by the way, for pointing this out. Like, this is the cleanest way I found for creating a static interface. If anyone knows of a better way, please reach out to me after the talk. But with that, let's take a look at an example view. So over here, we're going to do transform, a really important one. And basically, just like with ranges, we have maybe transform here as a view implementing our view interface. So just a warning, this is probably the kind of most complicated snippet in this presentation. I'll try to explain it as best as I can, but if you can understand, that's great. If you can, please reach out to me after the talk. I do think that this is the most fulfilling aspect of this proposal, so I'll give my best. But basically, the transform view takes as input 2 things. It takes an input view and a callable, right? And I guess we need to have some requirements for those. I guess the input view must be maybe-like as well. And the callable must be invocable with the object within input view. And the next thing, those 2 inputs somehow need to be retained within our transform view. And I have left this as a kind of black box for this talk. This is personally what I found the most challenging aspect of understanding ranges, so I don't think it's worth digging into this here. Instead, I want to spend a little bit more time and focus on the adaptation part, right? Let's check the bool operator. So the bool operator just defers to the bool operator of our input view. If that one is null, then we're null as well, and this is how transform works in general, right? For the dereference operator, well, this is where the transform logic is implemented. We basically need to invoke the callable onto the object within our input view. And now it might not be too obvious, but basically the implementation of the dereference operator for transform calls the dereference operator of our input view, right? So basically this thing over here, calling this triggers the execution to all the composed views, right? All the way to the source view. The source view being a concrete maybe type, something like stud optional, for example. And this is, by the way, how ranges views composition works as well. If you understand this, then you understand how ranges work, if you ever wonder. And I guess finally, we have a transform free function over here that takes a callable and returns a maybe closure. And maybe closure you can think as a function object that takes maybe as input and returns a lazy view. And it's basically just used to facilitate the composition of views. And you don't have to understand it beyond this. So this is the complicated part. Let's see with this design a few of the things that we can do. So this is example code or application code that can use this interface. So in the first 3 lines over here, we can define our unapplied closure, right? And this is a closure since we have composed 3 other closures and no maybe object. And again, as I mentioned before, this is going to be a function object that takes as input a maybe type. Then this thing on line 6, we can call onto some maybe object, right? And result here is going to be our lazy or else view, basically the last one from the composition above on line 3. On line 7, we can dereference the result and print it, right? And what we can also do is have a maybe to conversion to something concrete, stud optional in this case, right? And the last bit on line 6, instead of the function call, we can replace that with the pipe operator. So basically have maybe object pipe closure, and those 2 are equivalent, right? So basically we adopted the same design as for ranges for maybe types. Now, all of those are something we should be able to support with this design. What about types that don't fully comply with the maybe protocol? So we'll be speaking about maybe fine, but I want to show something simpler here just for illustrative purposes. So stud future can also be viewed as a maybe type in that we always need to check if the state of the future is valid before we call get, otherwise we really have UB. And that said, we can define our future view again as an implementation of the maybe view interface. Somehow we need to retain the future, we're not going into that. For the adaptation part, the bool operator just ensures that the future is valid, right? The dereference operator just calls future.get, right? And with that, let's see how our favorite double numbers example is going to look like. Actually, just one thing. We need to have a creator of a future under maybe views just to keep consistent. And now we can see how our double numbers example would look like with future. So here our input comes as a future string. And we start off by doing the maybe future adaptation. And the rest is literally the same, right? So in the end, we have this maybe to conversion to optional. And a piece of note, when this is requested, we're in essence calling future.get, which is going to block. So we're not really solving any of the async issues of future. We're just making the type a little safer while also allowing some sort of composition for future, which we didn't have before. I guess some additional notes we didn't have the time to go into today. I'm going to briefly go over them. I guess we can have more algorithms exclusively for the maybe protocol, right? Next, the pipe operator really has two flavors. We mentioned that before, but worth formalizing over here. So if we compose two closure objects to it, we produce another closure object. If, on the other hand, we produce a maybe object and a closure, that produces a lazy maybe view, as we saw with the or else example, right? I guess the maybe to conversion, we need to figure out exactly can we parameterize it. I can skip that. We also need to find the storage requirements for our views. I'm not going to go into that as well. This one is interesting. For the alternative case, should not be the only alternative, right? Basically, when we don't have a value. Well, if you want to support something like set expected, we probably need to customize the alternative case to have exception instead of null, right, for this thing over here. And the last bit is what we saw so far is just focused on producing results, right? So, and then maybe are all APIs to create this nice pipeline to produce results. And this is really what functional programming is all about, right? In reality, we might want to just unwrap a maybe and do something if there's anything there. So with P1255, this looked like that. We had our optional. We lift that via the nullable view to a range, and we subject that to a for loop. Compare that with an API specifically designed for maybe types, right? Probably something like maybe unwrap. In terms of lines of codes and end result, not much different, but in terms of expression of intent, I do think the second one is a little better. It's a personal opinion. But anyway, we went up on the side tour. I just wanted to discuss some of the important API considerations for this scheme over here. But to sum up this section, maybe types or nullables are like ticking bombs, right? They're all over the place right now. They're not as prevalent as ranges, but comparable. And to me, it makes sense to have a native maybe protocol and a bunch of algorithms for maybe types that make interaction with those safer. This brings us to the end. Thanks very much for attending. We don't have a lot of time for questions right now, but we're going to be here after the talk, so feel free to come and ask us. And as a concluding note, Bloomberg is hiring. We have our stand outside if you're interested, or speak directly to us. Thank you very much. Questions?
Yeah, that's very brave.
One question.
Hey folks, I don't know if this is on, but thanks for the talk. One sort of question on monads or functors in general. Let's say we have a functor that, it takes as an input STID variant of certain number of states and outputs a STID variant of another set of states. Was that sort of like would that categorically be a functor in that sense, or?
You're putting us on the spot. let us think. We can answer afterwards. It's one of those where it depends how you look at it.
It's like it's like transforming your state space under a function, which I'm not sure.
To me, variant doesn't necessarily fit all the criteria to be a functor. Like in a way, it is a wrapper type which you can unwrap, but at the same time, like the visitor pattern, right? Like you can have, each of those lambdas return something else, not necessarily the same thing. Mm-hmm. So to me, kind of treating it as a functor is like a little. You might shoot yourself in the foot in a way if you try to design some sort of like library for that. But yeah, I think it's questionable.
Right. Okay. Thank you.
So
most programmers are very comfortable with sort of imperative style control flow. That's what most people start learning to do, and they do it for a long time. When someone's trying to get more comfortable with sort of the monadic style of control flow, do you have any suggestions for how to get more comfortable with that?
Is this in terms of for yourself, or in terms of evangelizing to other people?
In my case, evangelizing to other people. A lot of the time when my team uses std expected or TL expected a lot. A lot of the time I tell our new people, hey, use this thing. And they're like, but this is confusing. And I'm like, it just functions.
I think from my personal experience with this stuff, I find the easiest way is when someone's actually writing code and they have a code view, you can say, hey, this snippet, what do you think of this other way of doing it, right? And if they say that looks stupid, then maybe you have an argument with them, right? But usually, assuming you have something that's sensible, it kind of speaks for itself, right? But I find code reviews are quite a good example because someone's already thought about the way they've done it, right? It means that they've already got a lot of shared context. It's easier to kind of bring someone on board rather than just kind of doing what we're doing here, which is kind of evangelizing to the crowd.
Yeah, to me, it's also about teaching the benefits of why is functional programming better, right? Like abstracting away this control flow, making it less error prone. Without this, I think just telling someone on a PR, like a junior developer, start using ranges, right? Like that might be a bit confusing. So that's important as well, I think.
In a lot of the monads examples I've seen, usually they're wrapping simple functions. I was wondering if at Bloomberg you guys have used monads to kind of control the architecture or the pipelines at the server level.
Oh, you mean for example, the microservice system, something like that kind of architecture level?
Yeah, something just much larger than say
so
convert an int.
Yeah. Right? Typically, it's kind of contained within some code snippets for now, just because rarely do we start working on an entirely new service, right? With people that all know about functional programming. So it typically kind of is contained within small snippets within some class or component. But even for those, we can kind of see the benefits. I read an article once, and it says that neither paradigm is a solution, right? Imperative or functional. Typically, you need to have some sort of mix of them, and that's probably the best thing you can get in reality. I might be wrong, but yeah. For existing systems, I think it's really hard to re-architect with one paradigm or the other fully. Yeah.
Cool, thank you.
Great talk. I was wondering, one of the things about functional programming is these pure functions that take in a vector and return a new vector. And you kind of said earlier in the talk, hey, we're not talking about the optimizations, but one of the things that I get my brain kind of wrapped around through this is, oh, okay, you're passing it into transform a vector of strings into ints, and then you're returning a new one, and that's very costly. What can you get into even a brief description of what the performance optimizations are to not do mega copies back and forth and return new objects all the time?
Yes, so I guess one thing, we haven't benchmarked any of this code, right? With the implementation of vector function we show, we do return new objects all the time. But something like ranges, for example, right, does things like lazy evaluation, right? So at no point in time, for example, you will have a new vector created until the very, very last of those, right? But even if you think about the optional case, right, you do have this case where you always need to check if the optional is null or not, right? As opposed to just doing it once at the top of your pipeline. So there is an inherent extra cost, which I think, if you're in a space that really matters, low latency or whatnot, it's just best to really kind of benchmark usages. And if you're in low latency, I don't think you would use something like optional or functors in your kind of hot path, right? Where the actual low latency is required. But typically, we use this all over our code base, and we also need to always keep monitoring our memory for the systems that we use, right? And we haven't really spotted anything, this is speaking from the real world usages, right? We haven't spotted anything that, would kind of indicate that any of those things are bad compared to the imperative alternatives. Yeah.
Cool, thank you.
Any more questions? All right, thanks very much, guys. Thanks.